Welcome all. Uh, Monica Verma ma'am, I will request you to please continue with the introduction and the session.
Yes, sir. So with warm greetings, I, Monica Verma, on behalf of CSA Department of Ph.D. DURG, extend my warmest welcome to one and all present here. This is our third day, ninth session of this one-week teachers training program. And it is indeed a privilege to have such a knowledgeable expert among us. And it was very enjoyable session throughout this day. And I feel much pleasure to invite Dr. Veera Kagita, our speaker for this session. Good afternoon, sir. As you, as you all are introduced with Dr. Kagita yesterday, where he taught us all about all Python data structure like list, tuples, sets, and dictionary, and we did hands-on too. So today he will be discussing on training and testing data visualization using Matplotlib. So as we have already done the NumPy and Pandas in the last session by Dr. Nipun Batra, so it will be helpful for us to learn this Matplotlib easily. So without any further delay, I would like to invite Dr. Kagita to share his knowledge with us today also. Thank you, sir.
All right. Thank you very much, ma'am. And very good afternoon, one and all. So as ma'am said, in this session, we're going to discuss about the training and testing and data visualization using Matplotlib. Right. So let's start with training and testing splits. How to perform training and how to perform testing will also. So I've checked your schedule also. So I've picked up the methods that is already covered in the previous sessions. So for better understanding, right? So without further delay, let's start the session. Am I clearly audible?
Yes, sir.
Yes, you are audible.
So is the screen visible to you?
Yes.
Yeah, thanks a lot. Right. So training and testing. So let's try to understand these two terms, training and testing, before we.
Dr. Rao, your voice is a little bit very slow. Can you speak
okay.
a little bit loudly, please?
Yeah, sure. Hold on for 1 second. Probably I have to change this. Oh, I have no option. 1 second. Is it better now?
Yes.
Sorry. Right. Let's try to understand the terms training and testing before we proceed it to apply for different learning techniques. So in any of these learning methods that we have seen in machine learning, like you might have seen regression, you might have seen classification, you might have seen different classification techniques and different regression techniques. Right. So they are basically to solve some purpose, right? For example, if you take the regression problem is to predict for the continuous values, like predicting the house price or predicting the temperature or estimating the number of cells. These are all the different examples of the regression. Similarly, if you take the classification problem, it is for a particular purpose. So like, for example, classifying a mail as a spam or not, or classifying an object as one of the classes, or whether there's a cancer or not, whether there's a moderate cancer, mild cancer, or classifying a mail to one of the folders, like primary, whether a mail should go to a primary folder or updates folder or social folder. This is an example of multi-class classification problem. Whereas if you take spam or not, it is a binary classification problem. Anyhow, any of these problems have some real world applications, right? So to solve that real world applications, we are trying to build some models, right? Like if you take the regression problem, we may have a linear regression model, polynomial regression model. I hope all these terms are not new for you. I hope you are familiar with all these terms, because I'm just using the terms relevant for your previous sessions only. So I'm hoping that all these terms that I'm talking are not new to you, like linear regression, polynomial regression. Similarly, if you take classification problem, there may be SVMs, decision trees, right? Logistic regression. So these are all the different classification problems, classification models that we use to solve some real world problems, right? Like regression or classification problems. Now the question is, you have all these models that you have learned from the training data, from the real world data. So how do you know that how well a model is performing? How do we know that? How do we know how well a particular model is performing, or how do we know that which model is better if we have multiple models for the same purpose? Right? We should have some evaluation measure, right? Right? And we should test that on new instances and see how is it performing, isn't it? So if you want to test on new instances and see how is it performing, you should have a ground truth for these new instances, isn't it? So for that purpose, what we do is that we take the whole data given to us and we divide that into training and testing data, right? So we just give the training data to a model. So to build a model, we use only training data and we hide this testing data from model building, right? So these test instances are new to the model. So these test instances are the instances where the model has no idea about. So we want to see how well the model is performing on these test instances and evaluate based on different evaluation measures. So in each of these models, each of these problems like regression, classification, there are some standard evaluation measures defined by the experts, researchers. Like for example, if you take regression problem, mean absolute error, root mean square error, like this, there are some evaluation measures. If you take classification problem, there are evaluation measures like Z1, 0, 1 error, precision, recall, F1 measure, right, confusion metric, accuracy. So like this, some standard evaluation metrics are defined for each one of these problems. And we want to see how well a model is performing with respect to these evaluation measures on the training and testing data. So why we want to see it on the test data? Because we want to see how it is performing on the new instances where the model has no idea about. Right. So that is why we are hiding this test data from model building, and we are using these test instances to evaluate the performance of a model or the hypothesis that we have built in any of the tasks. Right. Any of the tasks that you take, regression, classification, clustering, whatever the task that you take. Right. So let's try to understand that by taking some of the models that you have already learned. Right. So you have already seen regression, you have already seen classification. So I'm just taking these two problems and trying to take some of the models from each one of these problems and see how to perform training and testing with respect to these models. Right. So let's start with linear regression. As all of you know, that linear regression is one of the solution for the regression problem. So this is one of the model for the regression problem. So let's try to build a linear regression model for the data that is at hand. So these are the different libraries that I'm importing to perform these tasks. Right. I've imported NumPy library to do all the vectorized numerical computations on the data set, including the implementation of the algorithm. I'm also using matplotlib to plot graphs for better understanding the problem at hand with some visual aid. And sklearn.datasets I'm using to load toy dataset and to play around with our written code. So I'm not explicitly importing any of the datasets from the files in this case, but I have examples for them for that also. You can see that later. I'm using the some standard library datasets that is available in the sklearn library, and I'm just playing with them. And try and test split. This is very relevant for this session. Try and test split to divide the data into training and testing. So what we do, we divide the data into training and testing, two parts, right? We separate the data given to us to two parts, and one part is training, another part is testing. So now using this training data, we build our model. Once we get the model, we give the training data to this model and evaluate this model based on this training data and different evaluation measures that we have at hand. So according to our requirement, whatever the evaluation measures that we want to check, right? So it is very simple procedure. You take any machine learning model. This is a common framework that we use. We divide the data given to us into two parts, training and testing. Training data is used to build a model. Once we get the model, we give the test instances, that means the new instances, to this model, and we predict for these new instances, and we also have the idea about the ground truth, what the actual value is. So now we compare the actual value and the predicted value and see how much it is deviating or how accurate, how close it is to the actual value, how close the predicted value is to the actual value. So we want to compare this actual and predicted values and see how much they are deviating or how well they are close to each other. So this is what we want to evaluate, right? So very simple. So let's try to take one of the models and try to see how is it doing. So now I'm importing linear regression model. So sklearn is the library. From this sklearn.linear models, I'm importing linear regression. So linear regression is one of the solution for the regression problem, as all of you know. And I'm also importing the metrics, one of the metrics to evaluate the performance of this linear regression model. So there are various metrics. I'm just importing one of them to just demonstrate. So from sklearn.matrix, I'm importing mean absolute error as MAE1, right? So mean absolute error, all of you know, right? The difference, the absolute difference between the actual and the predicted. Pandas, I may not be using in this, but yeah, it is to make use of this data frames. If I use it, I might not have used in this, right? All right. So now, so let's try to build a linear regression model. So I have to take the data set first, and then I divide the data set into training and testing. Then I apply linear regression model. So this is the procedure that I have defined, right? So let me try to load a data set. So I'm loading a Boston data set. So in linear regression model, you might have seen, I'm not sure, but you might have seen one of the example of house price prediction, right? So given the information about the houses, like the features of the house, like for example, size of the house may be one feature, number of bedrooms of the house may be another feature, number of floors of the house may be another feature, or age of the home, age of the house may be another feature. Like this, each of the house is defined with some defined in a d-dimensional space, and the corresponding target values, target value is the price here. How much is the price of that house is also defined over n number of instances. So given n plus 1th instance, we should be able to predict the price of the house. So for n plus 1th instance, we only know the description of the house. Description of the house in a d-dimensional space, like what is the number of what is the size of the house, how many bedrooms are there in the house, how many floors are there in the house. Like this information is given for a new instance. So given this information, we should be able to tell what is the price of the house for this new house, right? So this is the problem precisely. This is a regression problem because price is a continuous value, right? So because price is a continuous value, this is a regression problem, and we are trying to solve this problem in this program. So I'm loading that data set. This is the Boston housing data set, which is already there in the libraries. So from sklearn.datasets, I've imported load Boston. I'm just calling that load Boston. So which returns this data set. So this function load underscore Boston returns the data set. So once that I receive the data set, I have to convert that into the required format. So I have to convert that into x and y's, where x is the input variables, y is the output variable or the target variable we call. So data set dot data equal to x is equal to data set dot data and y equal to data set dot target. So where x is the feature vectors, set of all the feature vectors, right? So matrix of all the feature vectors together we're calling it as x, and y is target variable, so vector of different target variables. So now I have x and I have y. X is the input variables and y is output variable. Now this linear regression models the relationship between the input variables and the output variable. Means what is trying to define a model, the output variable in terms of this input variable as a function of the input variables, and that function is linear in case of linear regression model. Okay, so I'm not going to in depth of what is linear regression because the current section's focus is not that, right? So just to relate, I am just giving you some hints, right? So but then my intention is not to go in depth of this linear regression model, right? So now given this x and y, I have to divide this data into training and testing, right? So that's what we do, right? We divide the data into training and testing, and we use the training data to build a model, and we use the testing data to test or assess the model. So now this x and y information is passed to this train test split that we have imported here, right? So we've already imported this train test split from sklearn.model selection. So I'm passing that information x and y to this train test split, and test size is 0.3. It means what? I'm taking 30% of the data randomly as the test data and remaining 70% as the training data. Okay, 70% training data, 30% test data. Here random state equal to 42 is an optional. It can be any number, not necessarily 42. It means what it says is that every time when you run, if you fix the random state, every time when you run this program, it will not produce a different training and testing split. So it would produce the same split whenever you run this program if you fix the random state to some number, right? So if you don't want this, every time when you run, if you want a different random selection, then you can ignore this random state equal to 42. Usually we ignore. Just for the programming, demonstration state, I have kept this random state equivalent to 42, right? So now I have training data and I have testing data. I have x train, I have y train, I have x test, and I have y test, right? Where x train is the set of features in the training data, and y train is the target values in corresponding target values in the from the training data. X test is the features in the testing data, and y test is the target values of the test data, right? So we have this data. Now I am calling this linear regression model that I have imported. So this is the linear regression model that I have imported from sklearn.linear model. So once I call this, it returns an object. So using this object, I fit a model to the training data. So using this object, I'm calling a fit function on the training data. So just underline this. I'm just using the training data here. I'm not using the whole data set, or I'm not using the test data set. I'm just passing the training data set here, x train and y train. X train is the feature vectors from the training data, and y train is the corresponding target values. So these are the input variables from the training data, and these are the output variables from the training data. And this linear regression models a relationship between the input variables and the output variables. The output variables are modeled as a linear combination of the input variables in case of linear regression. So now the model is built using this training data. So and the model is not visible for us, right? So if you want to access, there are some parameters you can access that, but you don't need that in general, right? So once you fit this model to the training data, and we use that training data and predict further test data. Right. So I use the same object and call the predict function on the test data. So only I am passing the feature vectors of the testing data, right? Test data. So I'm not passing y test here. Underline. Note that, because y test is the ground truth we know, and this function returns the prediction values for this x test. So once we get the prediction, we want to compare it with the test actual values. So y test is the actual set of values, and y prediction is the uh, predicted values given by the model, right? So this predict function returns a vector of predicted values. Right. So now I have the actual values that are there in y-test, and I have the predicted values that are there in y-predict. So I'm calling this evaluation metric that I have imported from sklearn.metrics. So from sklearn.metrics, I have imported mean absolute error as MAE1. I'm just calling MAE1, which is the mean absolute difference between the actual and the predicted. Sum of the mean absolute difference between the predicted and actual values. So I'm passing the parameters required by this mean absolute error. Parameters required by this mean absolute error are testing data and the predicted values. So these are the test values and these are the predicted values. Y test is the actual values, Y predict is the predicted values, and it returns the mean absolute error. Okay, so 1 second. Right, so it returns the mean absolute test error. I'm just printing that MAE is scalar MAE test error. Right, so MAE that I've got here is 3.162. Right, this is how you can divide the data into training and testing, build a model, and test your model on the testing data. This is the common pattern that we follow for any of these models. Right, we divide the data into training and testing, and we build a model. We fit the model to the training data, and we predict for the test data, and we call evaluation metrics required on this by passing this testing and predicted information. Then we just print that matrix. Right, very simple procedure. Right. So another one that the usual practice among the research group is the k-fold cross validation. So if you observe this training test split, you're randomly dividing the data into 70% and 30%. Who knows that random division may be biased to your model, isn't it? So based on one random split, you cannot say that your model is good or bad, isn't it? So there are different ways that the people to fix this problem. One of the solution is that you repeat this procedure for some reasonably good number of times. Like for example, you remove this random state. So every time when you run this time test split, randomly it divides training and testing data. So some random split. So you repeat this procedure for say for example 100 times, and 100 times you got this MAE error, and take the average of that, so which is more consistent and not biased to a particular type of data set. Right. So that is one way that people do. Another one is the k-fold cross validation. K-fold cross validation is that what we do in this k-fold cross validation is that we divide the data into k-folds. Suppose if I say 5-fold cross validation, I divide the whole data set into 5 folds randomly. 5 folds, 5 subsets of the whole data. So every time I take one of the fold as the testing, remaining 4 folds as the training. Right. So I repeat this for all the different folds. So in split 1, I take the first fold as the testing, remaining folds as the training. Similarly, in split 2, I take the second fold as the testing, remaining folds as the training, and so forth. So I repeat this because you're covering all the data in the testing, and take the average accuracy or error among all these different splits. Right. So the final evaluation is based on the overall test data. I mean, you get the test error from the first split, test error from the second split, and so on, and take average of all these individual errors. Right, that would give the final error. So this we call it as the k-fold cross-validation. This particular case is 5-fold cross-validation because you divided it into 5 folds. Suppose if you divide the data into 10 folds, then it is a 10-fold cross-validation. Right. So in general, k-fold cross-validation, you are dividing the data into k folds, and every time you are taking one of the fold as the testing, remaining folds as the training. Right. So this is the general practice that usually what people do, standard practice. Right. So to perform this, there is a method called cross-validation score from sklearn.model selection. We're importing this cross-val score, and hypothesis is linear regression. I just have to pass this hypothesis and data and number of folds here. Right. So cross validation score, hypothesis, what is the model? Model is linear regression here. X and Y is our data, and how many folds? Cross validation equal to 5, means 5 folds. If you want to do 10-fold cross validation, you can pass CV equivalent to 10 here. I'm just printing the scores here. You can see that, and this is the accuracy that I'm just printing, which is the mean of all the individual scores that I have got. So for 5 folds, each one of them is returning one of the score, right? So score dot mean gives the average of all these individual scores, which is the average accuracy. By default, it is, I mean, it takes the evaluation measure as the accuracy. I mean, whether the predicted and actual are same or not. It is very less chance in case of regression problem. That is why I might have got 0.35 accuracy. But usually in classification problems, you get a very high accuracy score. Right. But you can set your own score by using this scoring. Right. By passing scoring equivalent to neg mean absolute error. This is a mean absolute error is the scoring strategy that you are using, right? So like that, you can have a different scoring techniques. Like as you can see here, you can pass for classification. You can pass accuracy as a keyword, or balanced accuracy, top K accuracy, F1 score. So these are the different evaluation metrics from the classification problem, and from the clustering problem, and from the regression problem. You can pass any of these keywords as an argument to this function, and you can get the corresponding score, right? By passing scoring equivalent to the keyword, whatever the keyword that you want to pass. An average of all these individual scores that you have got is the average accuracy, or the average score out of all the different folds. This is how you can do k-fold cross-validation. So this is linear regression model. So you might have seen another model in the regression problem, that is polynomial regression, right? So polynomial regression is what you are actually transforming the data by generating the polynomial features, isn't it? So like this. So for example, if x is the original set of features, then you're generating x square, x cube, so on, x power n. So it means what? You are generating new set of features and then applying the linear regression problem on that. So that is a polynomial regression, isn't it? So this is the model that you might have seen in one of the sessions, one of the previous sessions, right? So to test this polynomial regression, I'm generating one of the data set, I mean a synthetic data set. So observe here, I have used the library data set, load Boston. Here I'm generating data set on my own, right? Like that, in different programs, I'll demonstrate different ways of importing the data sets from files, from the URLs, or from libraries, or by generating on in the model itself. So there are different ways that you can import the dataset. So here I've used a synthetic dataset to test this model. So dataset is x and sine 2 pi x. X is the feature vector, sine 2 pi x is the corresponding target variable. So sine curve is the underlying model from which I have generated this data. So, and added some random noise to it. So if you see, I'm randomly generating samples, which is x, right? I'm just normalizing them, sorting them, and this is y. sine 2 pi x plus some random noise I'm adding to it, right? And I just got x and y and returning x and y. So this is just generating the data set. Another important one in case of features is that generating the features, polynomial features. So suppose if there is only one input variable and degree is m, degree of the polynomial is m. So I have to generate x square, x cube, so on, x power m, isn't it? So like the way as you can see in the figure, right? So this is all set of instances with a given feature, and these are all the generated features. So this column is one generated feature, and this column is another generated features, and so on. This is the another generated feature, right? And it takes the degree of the polynomial as the input, which is m, right? So if m equivalent to 2, we generate only one feature, which is x square. If degree is 3, we generate x square and x cube. If the number of input vectors are 2, it means x1 and x2 are both are present, then the degree of polynomial is 2. Then we have to generate x1 square, x2 square, x1 and x2, right? So this is how you can generate the features, by calling the polynomial features and passing the degree to it, right? And just fit transform on x. So we're calling this polynomial features with degree dg. Dg is the input that we have got for this function, and we use this object and call fit transform on this x, which generates the polynomial features. So given x, it returns this matrix of this and returns the polynomial features. And this is a normalization function that we have why we require normalization to bring different features into the same scale. Here I have used mean square normalization. Means I am subtracting every feature from its mean and divide it by standard deviation. So this is the normalization. So I'm not going in detail of this because I'm not sure whether this part is covered or not, but for you to understand how it is applied, it is not required to go in depth of. The thing that you need to understand is that normalization brings the features into the different features into the same scale. Say, like for example, if you take the square feet of the house, which may be in the range of some 0 to 2000. If you take the number of bedrooms, that may be in the range of 1 to 5, right? So if you see these two features, there is a huge range difference between these two features. So what happens if there is a huge range difference between the features, then it takes a longer time to converge for a model. So to avoid that, what we do is that we perform some pre-processing on the data and bring these two different features into the same scale. Same scale, like for example, -1 to 1 or 0 to 1 or -0.5 to 0.5. In the similar scale, we bring them so that it will converge fast. So this is an attempt to bring the features into the same scale. What we are doing, we are taking one column, it means one feature, and taking every element, subtracting that element with the mean of that column and divided by standard deviation of that column. So that's what we are doing in this. I just implemented this normalization, mean square normalization. So we've got all the things that we require. So number of samples is 10. It means I want to generate 10 samples, and the degree of the polynomial is 10 I am giving. You can try with the different degrees and see how is it doing, right? So if you see, I'm just calling generate dataset, which I have already implemented here. So generate dataset, what it is doing, it is generating a synthetic dataset by randomly taking x and giving it to sine 2 pi x. So sine 2 pi x is the target value, x is the feature, right? So that is giving x and y. So it is returning x and y. So once I get x and y, I generate the features. I generate the polynomial features by calling generate features and passing the degree to it. So this is generate features, which is calling polynomial features, which I have already imported polynomial features, right? And returning a polynomial transformed x, right, with polynomial features. So this is x polynomial. I just normalized to bring them into the same scale, right? And then giving it to the training and testing, right? And It returns xtrain, xtest, ytrain, and ytest. Now, with the transformed features, I fit a linear regression model to it, xtrain and ytrain. And then I'm calling the predict function on xtext, and I'm just evaluating this based on mean absolute error. Ytest and y prediction I'm passing to it. I'm just printing that here. So you can see that MA is 0.16, just 0.16. To visualize what is the model and how the data looks like, I have plotted it here using the matplotlib. So this is a scatter of x and y, which means it gives the points like this, blue points, and then I'm just giving the title to it, which is the scatter plot pythonspot.com, right? So this is you can give whatever the title that you want to give. You can give like polynomial regression, polynomial model, right? And x label, just I'm giving it as x, and y label, y is given, but I can give 2 pi x, 2 pi x, okay. And this is the model, I mean that I am fitting to that on a x polynomial, and color that I'm using is red to plot that, right? So you can see that, right? So this is the data and this is the model. Red one is the model, and this blue points are the points. You can see that it is doing a pretty good job here, right? So you can vary, you can try it with different number of samples, like you can pass 100 samples and see how is it doing, right? You can right? So you can see what it is, I mean, almost close to the sine curve, isn't it? So from which we have generated the data. And you can also use the change the degree of the polynomial and see how is it doing, right? So degree equivalent to 3. So then also it is good. Let's see, degree equivalent to 2. So it's not that good. Degree equivalent to 1 means it is equivalent to the linear regression model, right? So which may fit the data something like this, right? So that's what. So this is how you can test your model, either linear regression, polynomial regression. Give me a second.
Some voice is coming.
Yes, yes, yes. That's why I'm closing the doors. My neighbors are fighting.
They are outsider.
Yeah, outsiders.
Okay. So is there no lockdown in your area?
Yes, sir. It is there. That is why all this quarrels.
Lockdown is open.
So
So
it
there
is
are
there.
certain advantages of lockdown. Suppose these people are doing work. If suppose there happens kind of lockdown, then they may not create any disturbances. Please continue, sir. Please continue.
Yeah. Now I think it is reduced at least. I've closed all the doors. One more is coming. Right. Sorry about that. All right. So yeah. So where am I? So this is how you can fit a model to the data and test your model by dividing it into training and testing. So let's see some more models that you have already covered, like SVMs and decision. I hope you have covered at least today. That's what from the schedule I have got, isn't it? So let's see them. So is it covered or not? I hope it is covered, isn't
Yeah,
it?
it is
Right?
covered, sir.
Yeah, SVMs, right. So let's see the SVM models and see how to test it, right? So these are the different libraries that I have imported. These are all common that we have already seen, right? So this is the model that we are trying to solve, right? sklearn.svm, I'm importing SVC. SVC is support vector classifier, right? So, and from sklearn.metrics, now this time I'm importing different set of metrics: classification report, confusion metrics. These are the different metrics that I'm importing from the classification, right? So so this is a model and these are the metrics. Now the procedure is common now also. I'm just importing the data set, which is a bill authentication data set from .csv file. So this is the file which is there in the current folder, .bill_authentication.csv. I mean, dot is the current directory, bill_authentication.csv is my file. And just to show you, I have just printed first few records of this data set. So this is a data set, and these are the 4 features of this data set: variance, skewness, cutoff, entropy, and this is the target value. Class information is the class information is given here. So this is a binary classification problem. So the class values are 0 and 1, and these are the different features of this data set. So let's prepare the data. So this is the data given to us, and this is how it is looking like. And I'm just preparing the data I'm just transforming the data in the required format. I just have to extract x and y from the data. So x is the matrix of all the feature vectors. So I'm just dropping the last column and the remaining things are taken as x. So from the bank data, I'm just dropping out the last column, which is the class, right? So this column I'm dropping out, the remaining things are taken as x, right? And y is just the last class, right? Bank data of class, right? So the last column is taken as the y, which is the target value, and the remaining columns are taken as x. Now I have got x and y. So I just have to pass it to training and test split, right? And the test size is, I'm just giving it 0.2, which means 20% of the data is taken as the test data and the remaining 80% is the training data. So after that, it returns 4 different things: x train, x test, y train, and y test. I just use the training data to train a model and test data while at the time of testing, right? So I just call this SVC. Kernel is equivalent to linear. It means I'm just using the linear SVM. So you can have a different options for this kernel, like polynomial kernel or BF kernel. Right? So kernel SVM you might have covered, right? Kernel SVM to separate the nonlinear data. Right, so you can have a different options for the kernel. Please do explore, like polynomial kernel you can have, or BF kernel, like that. There are different options for the kernel. You can pass any of that. If you pass linear, it is a linear SVM. Right. So once I get this model, I'm fitting this model to the training data. So I call this, if you observe, there is a common pattern in all of this. I'm just calling a model and using the fit function to fit a model to the training data and calling the predict function to predict for the test data. So common pattern. So you would take any of this, you just have to know the model name and the parameters that it takes. So once this model is known, you can create an object. Using that object, you can call a fit function on the training data and predict function on the test data. Very easy, right? So fit function on the training data, x train and y train, and predict function on the test data, which returns the predicted values. I know the test and test data, so I pass it to the confusion metric, which is one of the metrics that I have imported, right? From the sklearn.metrics, I have imported confusion metric. I have imported classification report. So I call both of them and pass y test and y predict for them. And this is the report. Confusion metric says how many of zeros are classified as zeros, 154 zeros are classified as zeros, and 1 zeros are classified as ones, and 2 ones are classified as zeros. So there is a confusion between 0 and 1. 0 and 1 are the classes, not the numbers. And 119 ones are predicted as ones, right? So that is a confusion metric. And there are other metrics also in the classification, like precision, recall, F1 score, support. so accuracy. So all this report is given in the classification report in this format, right? So this is how you can test any of the models, and this is how you can perform cross validation here. From sklearn.model selection, import cross validation score, like the same thing, and hypothesis is SVC linear classifier, and you can pass this hypothesis to the cross validation score, pass X and Y, and the number of folds that you want cross validation equivalent to 5. CV equivalent to 5 means 5-fold cross validation you are doing. And you can see that accuracy score, average accuracy score is 0.99. It means 99% accurate with a standard deviation of 0.01. So this is how you can perform. Similarly, you can also do kernel SVMs and multi-class SVM. So this is an example of linear SVM. Similarly, you can also perform kernel SVM. Like you can have a different kernels. Like for example, I'm taking a different data set now, not the data set that I've taken here. So I'm taking the data set of iris data set. Most of you may have idea about this iris data set. Iris data set is a data set about the flowers. So each flower is described with the 4 different attributes: sepal length, sepal width, petal length, and petal width. And the target value has 3 values. So there are 3 different flowers. So let's say 0, 1, 2. I don't remember the flower names, but there are 3 different flowers. Let's take 0, 1, 2 as the flowers. So this is the data set. I just briefly described the data set, and I'm just importing it from this URL. You can see that I have different ways of importing the data. So initially I have imported the data from the libraries. Then I have generated my own data set. Then I have imported data from .csv file. Now I'm importing the data from URLs, right? So this is how you can import the data from URLs. So read CSV, you pass the URLs and pass the column names. Here is the column name: sepal length, sepal width, petal length, petal width, and class, right? So this returns the data set to me, iris data. Right, I'm just printing this data to show you how it looks like. So this is how the data is looking like: sepal length, sepal width, petal length, petal width, and this is a class. So this is one of the flower, iris setosa. Setosa is one of the flower, right? So this is how the data is looking like. So from this data, I have to extract the data in the required format, X and Y, right? So I'm just dropping out the last column here, iris data dot drop, and taking the remaining columns as X, right? And I'm just taking out the last column, that is Y, right? I have both X and a lot of disturbance. All right. I hope my voice is dominating over there. Is it? I mean, are you facing difficulty? Are you facing difficulty? Is it a too much noise? Hello?
No, sir.
Anyone?
Sir, please continue,
Yes,
sir.
sir. Yes.
No, sir, it's okay. Please continue.
All right, because this is a place where I have no control, because I have come to my in-laws' home, and uh, I mean, I don't know any one of them, these neighbors,
No
so I
problem.
have no
No
control
problem,
of.
sir.
I'm sorry about that.
No problem. No problem,
No
sir.
problem, sir. Continue.
All right, thanks. Please understand. Sorry about that. But all right. So this is X and Y, and I divide the data into training and testing. I divide the data into training and testing, and now once I get the data in the format of this training and testing, once I get the data in the format of training and testing, I just fit a model on the training data. So I call the model SVC kernel equivalent to poly degree equivalent to 8. So you see that I'm just changing the kernel now. It's not linear now. I'm using a polynomial kernel at the degree 8. Right. right? So kernel is polynomial kernel and degree is equivalent to 8. Right, so the degree equivalent to 8 is the parameter required by this polynomial kernel. Right, so all the parameters required by this kernel, we pass it as a parameter to this SVC function. So degree equivalent to 8 is the parameter required by this polynomial kernel. So once I get this model, I feed the model to the training data, and once the model is built, I use the predict function to predict on the test data. And I'm just calling confusion matrix and classification report. As I have 3 classes, the size of the confusion matrix is 3 by 3, and this is the classification report. So right, so this is how you can build SVMs or kernel SVMs. You can also build multi-class SVMs. You might have seen different multi-class SVMs, right? Like one versus rest, one versus one, ECOC SVM, DAG SVM, binary tree structured SVM. All these are different multi-class SVMs. So usually the classification, SVM is for binary classification problem. To extend it to a multi-class classification problem, there are different ways that you can extend a binary binary SVM to a multi-class classification problem. So one of the solution is one versus rest classifier. So you can import it from sklearn.multiclass, right? You can fit it to training data. So I am not dividing it into training and testing data here. I've just taken some random samples and just to demonstrate it to you. So this is X and Y that I have taken, and I'm just calling one versus test classifier, and the base binary classifier that I'm passing here is SVC. So SVC is the binary classifier that I'm passing. On top of that, one versus rest classifier is implemented, and I'm fitting this classifier to X and Y and predicting for these new instances as it is shown here, right? So it is returning a predictions of 2, 0, 1, right? And similarly, you can do it for other classifiers also. An iris dataset, for example, I'm importing one versus one classifier and linear SVC, and I'm training and testing split one versus one classifier I'm calling, and this is the base classifier that I am passing and calling a fit function on that, and using a predict function on X test of 10 instances 0 to 9, and this is the results. So this is how you can test different models, right? So different models like regression and classification. So SVM, it is covered, so I've demonstrated that. So let's go to the decision trees also. Quickly, we'll wrap it out because it is already 4, and matplotlib we have to cover. So let's quickly wrap it up, this training and testing part. So this is the decision tree classifier from sklearn.tree that I'm importing. So from sklearn.tree, I'm importing decision tree classifier, and this is a testing and training split, and I'm just importing matrix. I'm also importing tree to show you how it looks like. I mean, to visualize. So this is the data, student pass fail data. This we have already seen. Self-study daily, number of hours, tuition monthly, number of hours, right? So these are the features, whether the student is a pass or fail. So this is the data set that we have at hand. Just to show you, I have printed few of the first few records, right? So I'm transforming it into the required format by dropping out the last column. Remaining columns I'm taking as X, last column I've taken as Y. Then I'm calling training and test split, which returns X train, X test, Y train, Y test. Now I'm calling the required model, which is decision tree classifier that I've already imported. As you can see here, decision tree classifier. I've already imported that. I'm just calling it, right? So I use this model and feed it to the training data, X train and Y train, and predict for the test data using the predict function, so which is returning predict. And after that, I call the metrics accuracy score on Y test and Y predict, right? So it is printing an accuracy of 1.0. It means 100% accurate on the test data, right? So you can, so this decision tree classifier, so you might have already seen that there is some metrics to split the data, isn't it? So what attribute should I select in the root node, and what attribute should I select in the internal nodes is decided by one of the measures, right? Like entropy, Gini index, like that. So by default, if you call decision tree classifier without passing anything, it takes Gini index as the impurity measure, right? So if you want a particular criterion like entropy, you can pass that as a input to this decision tree classifier. Criterion is entropy and maximum depth is 3, right? So you're not allowing more than 3 depth, which is one of the pre-pruning technique. So like that, you can pass the criterion that you want and build a classifier and fit it to the training data and predict for it. Accuracy here is also 1. Suppose if you want to visualize how the tree is looking like decision tree, you can call the plot tree on this classifier object that we have built here. So tree dot plot tree CLF, you can see this is how the data and this is how the tree is looking like. The condition at the root node is x of 1 less than or equal to 29.0 or not. If no, left side. If yes, right side. So at level 1 itself, it is terminating, and this is how the data is looking. All right, so that's all about the decision trees, and this is how you can test different train and test different models. So any of the models, the pattern is same. You divide the data into training and testing, and take the training data and give it to a model, and fit a model and predict for the test data, and call any of the evaluation metrics that you are interested to observe, and predict for the test data and see. Right. So let me close all this. That's all about the training and testing. So let's proceed to the matplotlib. So matplotlib is to visualize the things and to plot the different graphs. It is basically for the visualization. So this is how you can import this matplotlib Python plot as a PLT, right? So I'm just talking about this matplotlib.pyplot Python plot, right? So I've generated some data X, right? So I've generated 100 values in the range of 0 to 10 with the equal line space. I mean, the difference between them is equal, right? So this is how I generated, and this is how the data is looking like. I've generated 100 points, and these are those 100 points in the range of 0 to 10, right? So, and I'm plotting this x and x as a feature and np.sin x as the corresponding target value. So this is the curve. This is how it is looking like. So I'm plotting this x and sin x. So NP is the NumPy library that we have imported. So NumPy, just now you have finished. You might have idea about this. So in NumPy library, I'm calling the sine function, which is the sine of sine, sine cos, like that, sine of x. So x and sine of x. So which is generating a sine curve, as you can see here. So plot dot PLT is the object, I mean this library that we have imported, pyplot, from which we are calling a plot method and passing this x and np.sin x, right? So this is how it is looking like, right? It is generated, it has generated the sine curve. You can save this figure using savefig, right? You can save with this name linegraph.jpg, right? So if you want to change the color of this graph, you can set the color, like color equal to k is black, like color equal to red must be red, right? So like that you can, oh, what happened? So this is also giving a scatter. And now what happens here? Let's see. Don't worry about it. right? Right. So this is how you can change the color to different colors. R means red, blue, B means blue. Like that, you can change the color of the curve. Right. So you can also pass different numerical values. Each of the numerical values is mapped to one of the colors, like as you can see there. And line style also you can change. Line style equivalent to solid means the solid line it gives, and the line style equivalent to dashed, it will give the dashed line, right? So like you can see here, right? So these are all the linear lines that I'm plotting. X on the x-axis, x plus 0, x plus 1, x plus 2, x plus 3 on the y-axis, right? So color equal to k, which is a solid line style, right? So this one, right? And line style equal to dashed, line style equal to dotted, dash dot. So these are the different line styles that you can adopt and see, right? So these are the different colors also you can give, different line styles also you can give. If you don't want any color, it randomly picks the color. Right. So you can, I mean, there is a different way that you can pass these colors and line styles in plot. Like for example, if you pass this dash and R, this dash indicates a solid line, R indicates a red color. And similarly, this dash dash indicates a dotted line and blue indicates the color of that line. So this blue line, as you can see, you can map that. The first line is corresponding to the red line. The second plot is corresponding to this blue line. And the third one, dash dot, is the line style and G is the green, right? So dash dot is the line style and Z is the color of that. And colon C is colon is the line style and C is the color of that. Cyan is the color. So this is how you can use different colors and different styles to plot graph, to plot a graph, right? So that's one thing. And you can also pass, okay, let me execute this, sorry. So now if you see in any of these figures so far that we have discussed, we have not set any X labels, Y labels, or any inline labels for these figures, right? So how to set them, we'll see that. So suppose if you don't give any, it takes the range of this X randomly. Suppose if you want to set the limits of X, you can set them using X limit. So plt.x limit, this is the range for the x-axis, -1 to 11, and this is the range for y limit, -2 to 2, right? So this is how you can see that, right? It has started from -1, ended at 11, and this has started at -2, ended at 2, right? So this is the range that we have set. So x limit and y limit you can use to set the limits of x-axis and y-axis. Right. So, and similarly, you can also test, you can also set the title for the graph and the label. You can also give the labels information for the x-axis and y-axis. So x-axis description is set using x label method. So plt.x label, and this is the name that you want to give for the x-axis. I just give x. And this is the name that you want to give for y label, that is sign of x. And this is the title that I'm giving for this plot. So title method you can call, and the title that you want to set for this graph. So x versus sin x, right? So this is how you can set labels and the titles for the graph and limits of our x-axis and y-axis, right? So you can plot two different graphs in one plot, and you can also set the labels for each one of these curves, right? So if there are two curves in a single graph, So you have to indicate what is what, isn't it? So suppose if I plot sin x and cos x in the same graph, I have to indicate what is sin x and what is cos x, isn't it? So I have to say that this orange wala is the cos x and sin wala is, blue wala is sin x. To set that, I can use inline labels. So I just set the label to sin x here and label to cos x here in this case. So the label is the parameter that we use to set the inline labels of the different curves in the graph. So the label is the parameter that I use to set this, and dot legend is to display that legend here. So you can see this, right? It has shown this in the bottom left corner of this. You can also set the position of this legend also. You wanna, whether you want it to be at the center or you want it to be at the left right corner or left left bottom corner or top right corner, wherever that you want this to be, right? You have an option to do that. Like for example, here you can see legend location is upper center. So you can set that, right? Upper and center. Upper and right also you can do. Upper left also you can do, right? Lower center you can do. Lower left you can do. Lower right you can do. So you can set the position of this legend, right? And you can also give frame to this legend. Like if you see, you don't have any border for this legend in this case, right? So if you give an option of frame on equivalent to true, then you can see that now there is a border here, right? So you can set a border like this. You can see, right? Right, there is a border. So if you want a border for this legend, you can use an option frame on equivalent to true, right? So, and you can also have an option called n column equal to some number, the number of columns. So n column equal to 1 means it will be in the same column, right? As you can see here, right? There are, both of them come in the same column. N column equal to 2 if I set, so it has come in 2 different columns, as you can see there, right? And the DPI is equivalent to 500. So, I mean, with the DPI equal, you can save a figure with the DPI equivalent to 500. Right. So, all right. So you can also indicate where the point is there in the curve. Like for example, if you see these figures, we have no information that where the points are present actually in this curve, right? So if you want to indicate where the points are present inside that curve, so you can represent that using an additional one here. That is, here I have given this delta kind of this, you can say shift 6, if you press, you would get this cap kind of, right? So like that you can pass different options, like I can give O, right? So which returns the circles, and if I give delta cap, it returns this. So like this you can give different options. This is where the points are present, and you want to represent this graph with red color, and you want to use this solid line. Dash indicates solid line. Suppose if I give dot, sorry, dot may not be taken. Let me give another one. Dash dash. Right, dash dash is a dashed line. Dash dot may be dash dot line. Right, dash dot line. So the first one is the line style. The second one is to represent the points. The third one is the color. Suppose if I give B instead of R here, so you will get blue curve. Right. So like that, you can represent both the points and the graph as well, right? The curve as well. Right. So if you just want to plot the points, you can use the scatter function. So scatter of different points, x and np dot sine x. So this is how the points are scattered, right? So you can use a scatter to plot how the points are scattered in a two-dimensional space. Right. So you can even generate the data in different formats, like I mean, with the multiple attribute information you can represent, like the one you can see in the figure. So this here we are using the four-dimensional information. One dimension is X, another dimension is Y, another dimension is color information, another dimension is size information. Right. So we have four different dimensions represented in a two-dimensional space. So four dimensions, I'll tell you again. One dimension is X, another dimension is Y, another dimension is colors, another dimension is size. So we have four different dimensions represented in a two-dimensional space here. So let's see how to do that. So for this, I have randomly generated 100 points. So X is taken randomly, 100 points are generated randomly, 100 numbers between 0 to 1 are randomly generated, which is taken as X. X information for this 100 instances. And similarly, Y is also generated randomly, np.random.rand of 100, which is also generated, which also generates this points in the range of 0 to 100 points. And this is a Y information for this 100 instances. And colors also randomly generated and then mapped to some using some color mapping, CMap. Okay, so this is also a random number, and size also randomly generated because 0 to 1 will be very less for a size. I have multiplied them with 100. Right. So now just scatter X, Y, C equivalent to colors, S equivalent to size, and C map equivalent to some color mapping. Right. So it's not RGB. Right. So this is a scatter X and Y. Right. So X and Y we have already generated. Colors also we have already generated. I'm passing C to colors and S to size and C map equivalent to what is. And this is how it is looking like. These are the 100 points scattered in a two-dimensional space. So X-axis and Y-axis, color information, and also I have information about the size. Right. So different size points are represented with the different sizes in the visual plot. Right. So you can have a different color maps here. Here where this is used, but you can use different color maps. Like blues you can use. Right. It generates the color map something like this. You can use greens. You can use reds. Right. Like that you can use different color mappings. So it maps number to this colors. Right. So this is about the scatter and plot. Right. We can also build histograms. Usually we require histograms in most of the applications, right? So you can build histograms. So for that I have randomly generated 1000 points using the normal distribution, random, and I'm just plotting and calling this histogram. Right. So it generates so it generates this histogram as you can see. So there are different options that you can pass to this histogram that we're going to see in the coming in another file. Right. So you can also give two-dimensional histogram, hist2d using hist2d. So for this, I have generated two-dimensional data x and y using multivariate normal distribution with mean as 0, 0 and covariance as this. And I've generated 10,000 data points. So I'm just calling this hist2d on this x and y, and the number of bins I'm using is 30. Color map is equivalent to blues. Right? You can see this color map, right? The dark blue means there are more number of points in that bin, and the light blue means there are less number of points in that bin. So this is how the data is distributed in two-dimensional space. So out of 10,000 points, this is how the points are distributed in a two-dimensional space, right? The dark blue, it means that there are more number of points at that bin. Light blue means there are less number of points. So this color mapping is, color bar is indicated here at the right side. You can see that, right? Very dark blue means 140 points. Very light green means 0 point. Light blue, sorry. Dark blue and light blue means 0 points. So, and the color information with the corresponding the number of instances is given here in the color bar right side. So to do that, you can use plt.colorBar. You can call color bar. Right. So this is how you can draw a two-dimensional histogram. Similar, I don't know whether these contour graphs are discussed in any of the sessions or not, but you can use a contour. So I'll not go in detail of that. I don't want to confuse you, but you can use, those who have idea about contour graphs, you can use a contour to represent the three-dimensional space into two-dimensional like this, you can see. So 3 dimensions x, y, z are represented in 2 dimensions like this. It's like a top view of 3 dimensions, right? So if you have 3 dimensions, if you want to ignore one of the dimensions, right? Like for example, if you look at the 3 dimensions from the top view, you can only see 2 of the dimensions, isn't it? So that top view is given here in terms of the contour graphs. Right, so let's proceed further. So 10 more minutes we have got, but I may take 5 or 10 minutes more. I hope that is fine. So this curve plotting we have already seen, right? So how to test, how to add labels, how to add titles, all that we have seen, right? You can also even specify the width, line width of these. Like for example, you can specify line width width equivalent to 10. Okay, so you can see that, right? Line width is increased, right? So one of the things. So you can set your own line width. You can set the line color, and you can set the line style. All that we have already seen. This we have missed line width in the previous demonstration. So you can set the line width, you can set the color, you can set the style, you can set the inline labels, right? So all that we have seen. Okay. All right. So let me check. Like label equivalent to sin x. Right, we have got label, right? Sin x. Right. So this is how we can set. And suppose if you wanna plot multiple graphs in a single graph, right? Multiple graphs in a single figure, right? So multiple graphs in a single figure, you can use the panels like this. You can see, right? Two different plots are given in a single figure, in a single row. You can similarly give in a single column, or you can split it into 2 columns or 2 rows, 3 columns, 2 rows. In any way it is possible. So let's see how to do that. Right. So for this purpose, you can create a subplot. So this is how you can create a subplot. Subplot of 1, 2, 1. It defines 1 row, 2 column panel, activates figure 1. So 1, 2 means 1 row, 2 column panel, and comma 1 means it activates subfigure 1, subplot 1 in that, right? And similarly, if you call subplot 1, 2, 2, it means defines 1 row, 2 column panel and activates figure 2. It means the second figure, right? So I'm just plotting cos curve in subplot 1, which is this, right? And using red color and solid line here, right? So red color and solid line, which is this, the first figure in the first position. And the second position, which is this is the information for that second figure, right? So here I'm plotting a sine curve with blue color and solid line. So suppose if you want to change this to dashed line, you can pass double dash here, right? So this is now a dashed line. Suppose you want to change this to some star, you can pass. Now you can see that, right? It is a star, right? Like you can also give different things. You can give O also. Like this, different options can be given and line to change the line style and the color, right? And let's see that suppose if I change this to 2 2, it means 2 rows and 2 columns I am creating, and I'm keeping this figure at the first location. And 2 rows, 2 columns, let me keep this in the fourth position. So then how is it looking like? You can see that, right? So this is the first position. The second position we haven't kept anything. Third position also we didn't keep anything. And fourth position we have kept this sine curve, right? So this is how you can create a subplots, right? So like this you can create. Suppose if I keep this in the third position instead of fourth position, you can see that, right? Suppose if I keep this in the second position instead of third position, right? Right. So you might have understood that how to keep these subplots in the overall figure. So you have to create a this panel of certain number of rows and certain number of columns. So this is the information where you pass this number of rows and number of columns of the panel. One row and 2 columns, and this is the position where you want to subplot this. All right. So this is how you can do that. And then scatter plots, right? So how you can scatter the different, we have already seen scatter, but multiple, if you have a multiple groups, like points are belongs to different groups. So how do you pass that information, and how do you represent different points from different groups with the different colors or different labels, right? So like this. So for example, yellow squares are represented is a one group, stars with blue are one group, diamond reds are one group, right? Like that we have a different colors for different group of labels, right? So let's, for that, let's generate a data set. Let's generate a data set and try to plot that data. So for that I've used sklearn.dataset. I'm importing make blobs, right, with some center. I mean data is scattered around the center only, like if you pass the some center information. So make blobs, it creates a blobs like structure to the data points. So if you pass the number of centers to be 3, it creates 3 blobs, right? So make blobs, number of samples that we want to generate is 100, number of features is 2, centers are 3, random state equivalent to 4. It is to generate the same state every time, but you can change the random state. It's not, you need not fix that to 7, right? So now the data is generated. Now we have to plot the different groups differently. So for that we have to use the group information, right? So all the coordinates, x coordinates of group 0 are taken here, all the y coordinates of group 0 are taken here, right? So this 0 means x coordinate, this 1 has y coordinate. As you can see, there are only 2 number of features, 0 is x coordinate, 1 is y coordinate. And this group equivalent to 0 gives the group information. D of 1 gives the group information. D of 0 is the coordinates. So from the coordinates, we are accessing x and y coordinates again. So x coordinate is 0, y coordinate is 1. So for group 0, all the x coordinates are here, all the y coordinates are here. So all these points now we are plotting with a yellow squares. So y means yellow, S means square, right? So label I'm giving it to this is group 0. Similarly, I'm extracting the X labels of group 0, sorry, group 1 and y coordinates of group 1, and I am representing that with magenta stars. Right, magenta, is it magenta? Yeah, magenta stars. And group 2 x coordinates are extracted here, group 2 y coordinates are extracted here. I'm representing them with red, D for diamonds, right? And I'm labeling them as group 2, right? And I'm setting x ticks to now different information I've given. See here, I'm just not passing the range, I'm just exactly setting the ticks, right? 10, 6, 2 and minus 2, 10, 6, 2 and minus 2. Similarly, y ticks are set to minus 15, minus 5, 5 and 15, right? So, and so you can see here, right? I'm annotating them with squares, stars and diamonds. So this annotation you can see in the figure. You can see it here, right? We have annotated it with squares here, stars here, diamonds. And we also pass the position where I want to annotate, right? So I'm just executing this. So this is how it is looking like. Suppose if I want to annotate it at minus 12 and let's say 2.5, just observe that figure will change now slightly. The squares are here now at this position. You can see my cursor, right? Can you see my cursor? Anyone?
Yes, sir.
Okay, so squares are annotated here. Now if I want to change the position of the squares to minus 12 comma 2.5, you can see now the squares are here at this location. Right, so like that you can annotate different groups with the different labels, as you can see here using the annotate function. And similarly, you can fix the location of this legend also, right? So this I've already shown you, but here you can see that we have fixed the position to lower left and the number of points equivalent to 1. So in the legend, how many points that you want to have? So 1 means 1 point only we have. Suppose if I set this to 2, then you can see that, right? We have 2 points in this legend, 2, 2, 2, 2 and 2, 2. Right, so this is how you can set the location and set the number of points in the legend also. Right, next, histograms. Suppose if I want to generate histograms kind of like that, you can see, right? Right, so how to do that? For that, I've randomly generated 500 data points with different means. Since location equal to 0.0 means this is the mean of that data, and scale equal to 1.0 means the standard deviation of this data, right? We have generated the data using normal distribution, and normal distribution takes 2 parameters, mean and standard deviation. So location is the mean of the data, scale is the standard deviation of the data. So with the different means, I have generated 2 different data sets of size 500 each. So one is X, another one is Z. So I'm just building an histogram, right? By passing this X and Z, and histogram type, I'm setting it to bar, right? And colors are, I'm giving C and D, right? So C means cyan, B means blue. So if I execute this, so this is how it is looking like. So this is one histogram with mean 0, as you can see here, another histogram with mean 3, right? Similarly, if you want to change the histogram type to step instead of bar, you can set. So this is how it looks like, right? So this is one histogram and this is another histogram. All right, so if you want to just plot this individually also, that is also possible. So let me just show you one X. Ma'am, is it okay if I extend it for 10 more minutes, 10, 15 more minutes?
Yes, sir.
Okay, thanks a lot. So one histogram itself you can print. So you can see this, right? So this is the histogram. Right. So you can give different options like histogram type, stacked equal to false or not, fill equal to false or not. So like for example, if I pass this fill equivalent to false, fill equivalent to true, let me, this is already false. So now it is filled, right? Now fill equivalent to false means it will not be filled. It is transparent. And similarly, you can also pass density equivalent to true or density equivalent to false. So density equivalent to true, just observe the figure, I'll make the density to true. Now the density is false. So earlier, if you observe the range of the values, which were in the range of 0 to 175. Now if you see, this is in the range of 0 to 0 to 0.4. So density gives the number of items at a particular location divided by the width of that bin, right? So which is given, which is summarized as this frequency density, as you can see in the y-axis. Like that, different options we can explore to plot the histograms. Similarly, you can also plot horizontal bar graphs or vertical bar graphs. So this is another thing that we usually do it, right? Bar graphs. So how to do this? For this, there is a method called bar H, which is a horizontal bar graph, bar, which is a vertical bar graph. So bar is a vertical bar graph, bar H is a horizontal bar graph, right? So for this, I have used an iris dataset. I am loading iris dataset. I am taking average of the individual features. So individual features average is taken and standard deviation is also taken, range of them also taken. So range is in the range of 0 to 3. I mean 0 to 4, which means 0, 4, which means in the range of 0 to 3, right? So I'm taking subplots and plotting the horizontal bars, right? So range, which is in the range of 0 to 3, average I am plotting, and color I am assigning is red. X error is the standard deviation, right? And alpha is 0.4 means standard deviation. Align is the center, means center alignment, right? So you can align center, you can align it to edge also. Now to make you realize, let me change the different options and let you understand this. So let me change this to green. So this is the green, right? So this is the color of the graph. So right, let me change the standard deviation. Standard deviation is this one. This one line you can see, right? So this is the standard deviation of this, and average we have plotted in terms of the graph. And this is this black line is the standard deviation. So X error is standard deviation we are setting because the graphs are horizontal here. So suppose if I set Y error equivalent to standard here, right? So you can see that the errors are in the vertical bars, right? Vertical lines. That's why, because we have horizontal bars, we have to set the standard deviation to X error here, right? And alpha 0.4 means this is the transparency of this graph. Suppose if I set the transparency to 0.9, which will be very dark, you can see that, right? Suppose if I set the this to 0.2, it will be very light, as you can see here, right? And align center and align edge are the two options. You may not realize if I give separately. So let me give it in the same thing and to make you realize. You can see that, right? So green one is fixed to the edge and red one is fixed to the center. All right. So this is subplot to vertical bars, titled as vertical bars. Same thing. Only thing is, instead of bar H, I'm just giving bar here. Everything else is same. Right? Every other option is same. Only thing is, another thing that you have to remember is you have to fix it to y arrow here, because this is a vertical bar. And this is how it looks like, as you can see here. Similarly, you can also visualize the images in a subplot kind of structure, like as you can see here. Suppose if you want to show the multiple images in a single frame kind of, single image kind of, this is how you can show, right? So you use subplots with 2 by 3 size, 2 rows and 3 columns, and this is the place where you are fixing a particular image. So from this data set, you are fetching the images and reshaping them to 64 by 64, and color map is gray you have used, interpolation is the nearest interpolation you have used, and this is the title that you are giving. You're taking the target value and adding it to the subject. Subject information is present in the title, target value actually. And you are setting this plot.access to off. If you don't set it this, unnecessarily this X-text will be appear like this. Right? So that is why we are setting this access to off. Right? So now no access are present, as you can see there. Right. Similarly, if you want to load digits and plot that also, the procedure is same, as you can see here. Right. And this extent specifies the bounding box to which it belongs to. Right. So this can be visualized here. Right. Extent 0 to 8 and 0 to 8. So the extent that we have given here is 0 to 8, 0 to 8. Right. That's all about the matplotlib. If you give me some 6-7 minutes, I can finish this pandas also. Okay, I'll quickly go through it. You can use the pandas to draw box plots and histograms. Okay, I think it takes around 15 minutes. Let me stop here. So that's all about the matplotlib. If you have any queries, I'll take. Otherwise, we can wrap this session. Any queries?
Please raise question, participants. Professor Neeraj has raised question during this presentation. So, Mr. Neeraj Kharia, you may ask question what you have during the presentation.
Sir, can we have a discussion on AUC and ROC curve as well?
I don't have ready-made for them right now, but yeah, you can plot them. That's not very difficult. Because we don't have time, and I don't have premium for that. Let me. You should have asked me 10 minutes before at least. I would have. All right, I'll give you link at least.
Thank you, sir.
For you to yes, yes.
Thank you. Any more participant? Actually, this session must be very healthy. Okay, if you will not ask any question, then there is no sense of this FDB program. Actually, this lockdown online teaching training program is very much important to enrich your value in teaching, to enhance your value, to enrich your value knowledge. That is most essential. If you interact the speaker, then definitely it will be more beneficial for the student. Basically, the objective that you have to transfer your knowledge to the students. So, really, your presentation was very good, and it was very, you can say, I can say this kind of, you can say, enlightening speech. Okay, we have learned a lot because this is your second session. Yesterday I have listened, today also I have listened. We have covered many aspects of the training and testing data visualization using Matplotlib. So over to Partha Rao.
Yes, sir. So I thank Rao sir for his um, detailed explanation of all the uh, functions available in the Python library for managing the data and to visualize the data. Thank you very much, sir. So I will request Verma madam to conclude the session.
Thank you, Rao sir.
Monica Verma, madam,
Ji, sir.
have you point out areas which are covered by the various speakers from this session 7 to session 9? Have you
Yes, sir.
pointed out?
In the session 7,
So it will be better that if you will read out those brief points before
okay.
closing this day.
Sir, in the session 7, Dr. Udit Bhatia has covered the classification algorithms that are decision tree and support vector machine. And then in session 8, Dr. Nipun Batra has shared his knowledge in NumPy and Pandas with Python. We have done hands-on on that. And now we have learned the matplotlib and also learned that SVM and decision tree in Python. All the
Actually,
functions of Python, different packages of Python have been discussed very well.
मोनिका मैडम, अपन
Yes.
लोगों को क्या है कि जैसे जैसे सेशन 7 रहा ना, तो सेशन 7 में उसमें अपन ने क्या क्या कवर किया थोड़ा सा वो बताने की जरूरत है. कई बार क्या पार्टिसिपेंट आगे पीछे जाते हैं ना, जैसे सपोज मैंने नोट किया है, मैं थोड़ा बताऊंगा आपको. On session 7, decision tree, trend visualization and make prediction, basic terminology, measure of heterogeneity, impurities, he has covered. Given the various examples, calculations, Gini processing about how it is pure and impure, and support vector he has covered in the session 7. So these are some of the silent points. In the session 8, Professor Nipun Batra ji has covered the points related to this Python theory,